Okay, this lesson is on equilibrium constants. So we've talked about equilibrium as far as rates, how the equilibrium rates, Le Chatelier's principle, they're going to be, the forward and the reverse are going to be equal to each other until you apply a stress. And then the reaction's going to fix that stress by either making more product or more reactant. So equilibrium constant is going to be a value that tells you initially whether or not you're going to have more reactant or more product from the onset before you even start doing the reaction. So it states that at a given temperature, a system will reach a state in which a particular ratio of reactant and product concentration has a constant value. So this constant value is going to be what tells us whether we have more reactant or product once we have reached equilibrium. Ratio means we're going to be doing some division. So if we take our general equation here, AA plus BB reversibly yields CC plus DD. The capital A and B are going to be your reactants, the capital C and D are going to be your products, and the lowercase letters are going to be your coefficients there. So if we take this reaction and apply the law of chemical equilibrium to this, you're going to get an equilibrium constant expression. So the expression is just going to be the setup, not the actual solving for the value. So we're going to get KEQ equals C to the C times D to the D divided by A to the A over B to the B. So what we have done is we have taken our substances, we have put our products in the numerator, put our reactants in the denominator, and raised each one to the power of its coefficient. So you can see where those letters have been placed. So your KEQ is the ratio of product concentrations to reactant concentrations, with each concentration raised to the power of its coefficient. If you get a KEQ that is large, meaning it is greater than 1, then that means that your numerator value is larger than your denominator value. And remember, in our numerator, we're our products. So this means that products would be present in larger amount than reactants. If your KEQ is small, or less than 1, that would mean that your numerator is smaller than your denominator, and your denominator is where we have our products. So, reactants, I'm sorry. So that would mean that's where your reactants are present. So you would get more reactant than product. And that is not a favorable KEQ. Typically your goal is to get more product. So let's look at an example. We have ammonia plus oxygen reversibly yields nitrogen dioxide plus water. The first thing we need to check is this reaction balanced? And the answer to that is no. So let's take a second to balance this reaction. We got 1 and 1 nitrogen, 3 and 2 hydrogen, 2 and 3 oxygen. But since oxygen's by itself, we're going to save that one until last. So the only common thing between 2 and 3 is 6. So we can give this 3. That's going to make us have 6 hydrogen now. And 3 plus 2 is 5. So we're not going to be able to get an even number there. So let's get that 3 out of here. Maybe make that a 6. So that gives us 12. Now we have an even number of oxygen. So when we go to divide by 2, that can easily be done. So to get 12 over here, we need to put a 4. That makes us have a 4 in front of the NO2. So now to count up our oxygen, we have 8 plus 6, that's 14. So 14 divided by 2 is 7. So if we go and check, we have 4 times 1 is 4, 4 times 1 is 4, 4 times 3 is 12, 6 times 2 is 12, 7 times 2 is 14, 4 times 2 is 8, plus 6 times 1 is 14. So now our equation is balanced. So at equilibrium, concentrations were found to be ammonia is 0.921 molar, oxygen is 0.763 molar, and nitrogen dioxide is 0.157 molar. Water is 0.384 molar. And they want to know what is the equilibrium constant. So the first thing we need to do is set up our expression. So KEQ, remember products are going to be in the numerator, and since we are referring to concentrations here, we're going to have to use square brackets. So NO2, and we're going to raise it to the power of its coefficient, which in this case is 4, times H2O raised to the 6th divided by NH3 to the 4th times O2 to the 7th. So that is our expression. Once you have that, you can plug in your values. So NO2 here is 0.157, and that's going to be raised to the 4th, times water. Here's our water. That is 0.384, and we're going to raise that to the 6th. Make sure if you're going to type this all in at once that these are in their own little sets of parentheses here, the numerator and the denominator. Ammonia is 0.921. That's going to get raised to the 4th, times oxygen, which is here, is 0.763, and that's going to be raised to the 7th. So now when we go to type that all in, 0.157 to the 4th, watch your parentheses on here, it's going to get tricky, times 0.384 to the 6th divided by 0.921 to the 4th times 0.763 to the 7th. Hopefully I've typed this in correctly. We need 3 sig figs, so you should get 1.80 times 10 to the negative 5th, and this is going to be unitless, so this would not be an equation where your products are favorable because it is less than 1.